Well, hi, everybody. I'd like to introduce Laure Zanna from NYU, and she's been focusing on modeling, while the climate focusing on kind of like the atmosphere, ocean interactions. Yeah, welcome, Laure.
Great. Thank you very much, Greg, for the invite. And thanks, everybody, for joining. I'm definitely very excited to present to this audience. So I hope I give you a bit of a flavor. And so I'm going to start with some movies on how we've been using AI to try to accelerate ocean and climate model development, but basically trying to solve big challenges in ocean and climate in general. So trying to understand how kind of scale interact with one another, as you can see kind of playing in those movies. So, the effect of turbulence on large scale transport in the oceans and atmosphere is really kind of one of the holy grails that we're trying to tackle. So today, what I'm going to do is just kind of highlight a few examples of the. Oh, yes.
We're seeing your editor view, and you're trying to present your presentation.
Okay, so let's try again.
If anything, if you share one screen, doesn't mean you share the.
How about that?
No, still see the editor. I think you have to share.
Still see the editor? Okay, hold on. Let me stop sharing. Okay. Okay, I'll see that. How's now?
Perfect. And now I see.
Right.
Oh, it's beautiful.
Yeah. Okay. Great. Sorry, everybody. So at least now I'm still kind of letting the movies play for a second. But yeah, so basically what I'm going to talk about is kind of this scale interaction we're seeing and how to use different type of tools to accelerate climate model development overall. So I'm very lucky, of course, to be here and presenting, but this is actually teamwork. And this is kind of a large group of scientists across multiple institutions in the US and France. And that includes, climate model developers, people like me who are kind of, domain scientists to some extent, and people who actually develop AI tools. So really all of us kind of working in concert to try to reimagine the way we do climate modeling with data and AI. Okay, so I'm sure I'm preaching to the choir with this audience, right? So the AI weather revolution has been around. You can pick up any newspaper nowadays, and you'll see something about breakthroughs in AI for weather forecasting. And here is kind of a simulation coming out of ECMWF, which is center in Europe, having their own AI forecast simulators that they're now using, routinely. The same way they use their original numerical weather prediction. So, everything has been starting and accelerating in a matter of a few years. So it's actually a slide from Stefan Rasp at Google showing the type of, AI weather model that I've been basically using what we call reanalysis, which is basically a combination of observations and model to learn to fully emulate, how the atmosphere is evolving and trying to make forecasts out of it. And so you can see it kind of started kind of slowly, 2018, 2019, but then now you can see the number of AI weather model is kind of, rapidly growing, but so is kind of the skill that you can get out of those models. But it's been really kind of incredible to see move so fast with such high skill to actually predict the weather over kind of shortish timescales. So now, as mentioned at the start, right, I'm focusing on the oceans. The ocean is a lot slower than the weather timescale of days to weeks. But I want to give you a little bit of context, right? Why do they matter in the Earth system? So first, if I look at the surface of the planet, right, about 70% of the surface of the planet is actually ocean, right? So it's actually water. It's about 4 kilometers deep. Right, so it's kind of an interesting body of water. But just to put things in perspective, the top 3 meters of the ocean contains as much heat as the whole atmosphere, and the top 50 meters contains as much carbon of the whole atmosphere. So it's a pretty massive reservoirs of heat, carbon, oxygen, and so on. So it's a little bit of the lungs of the climate system. It can breathe in and out different tracers. But what it can do as well is to actually move it around. So it can move momentum, heat, carbon over great distances. And so the simulations that you see here shows you a lot of small scale turbulence, but also a lot of large scale currents like the Gulf Stream, for example, or tropical waves that actually can carry things over the entire basins in the Pacific. And this is really kind of a feature of the ocean, is that transport can happen, can be quite slow, but it happens over a wide range of scales. So again, just to give you context, the type of scales that we're talking about here, when we talk about the large scale currents, we're talking about thousands of kilometers, right? And it's usually forced by winds, by freshwater fluxes, by heat fluxes at the surface of the oceans. But those large scale currents usually break into kind of smaller scale turbulence. And so some of those are called mesoscale, for example, just to give you an idea. They're 10 to 100 kilometers in scale that derive their energy from the instability of the large scale. And then you go back to kind of smaller and smaller, scales. So some of them, again, are kind of generated through external forcing and through the turbulence of the fluids. And we go down all the way down to meter scale and timescales of minutes. So what we're spanning here is meters and minutes all the way to thousands and kilometers with, basically transport that takes years to decades. So if you think about the type of simulation that you would need, because all those scales interact with one another, dissipation and small scale mixing actually impart the large scale transport, right? So you really kind of need to span a wide range of scale and run your simulation for a very long time to actually understand how the ocean interact, with the atmosphere, but also how it interacts with different scales. And of course, the fact that, as we mentioned, right, the ocean can transport and, take up heat and carbon, it will have an impact on global scale, not just the local scales. So how do we usually typically do climate modeling to actually capture all those scales? Well, we take, Newton's law, thanks to ChatGPT for this little schematic, right? And we can actually, extract all the processes that matter, and then we discretize them on a grid. And then we numerically solve, the equations of motions for the ocean, for the atmosphere, and all the other components of the Earth system. So here's a simulation from GFDL, which is a lab in Princeton that has been developing climate models for a very long time, part of NOAA. And here we're seeing a simulation of sea surface temperature in a 1/12 of a degree climate simulation. So 1/12 of a degree for the ocean, that means that the grid box size, so the horizontal grid of the ocean is about, 10 kilometers, something like this, right? Of course, it varies its latitude. But what you can see is the Gulf Stream kind of detaching here from the US East Coast, lots of turbulence. And this turbulence, again, kind of re-inject momentum and energy into the large-scale transport, accelerates the flow. And it's a pretty major current, right, as we know. And again, all the scales interact in different ways in different parts of the ocean, but that's really kind of the way we simulate, the ocean, but the ocean as part of climate in general. And now, as I mentioned, right, I told you that this simulation, which actually is, maybe 15 years old, I think, or something like this, maybe even a little more, it's extremely expensive, right? And you can only go down to 10 kilometers because, again, it is extremely expensive. So we're missing a lot of scales, right? There's a lot of things that are happening below that scale that we're not resolving. And so why use simulations overall, right? So one reason is because I'm trying to understand something, right? And that's usually, in the academic world, one could say, and I think in general, all of us want to understand how different parts of, the climate system are working. And there's a lot we don't know, right? Because to some extent, we don't have enough observations, because again, we need to span a wide range of scales, both temporal and spatial. And again, it's a very complex, non-linear, fluid dynamics problem. So there's still a lot to understand, and simulations and theory have been great to help us kind of advance that. Second reason is, of course, to make predictions, right? So given the state today, what might be, the prediction of El Nino? So that's, for example, one of those graphs that use different type of models that try to predict what will be the sea surface temperature anomalies in the tropics. So one of the big modes of variability in the climate system, right? Which is kind of a little bit of a self-sustained coupled climate mode. So we use models to actually initialize prediction and see what might happen over the next few months. And then the other reason we use simulation in general is to ask questions. What if I were to change, the amount of greenhouse gases in the atmosphere? What if I were to remove it? And then we could actually figure out what would be the temperature anomalies as a function of time in those simulations, right? And you can think about other type of scenarios. We like to think about what might have happened, in the past if the glaciers didn't melt the way they did. So it's really kind of trying to be, hypothesis driven to some extent and explore the range of possibilities, that the oceans and climate in general could look like. Now, going back to the compute, right? Because compute is still always a little bit of a limitation for us. So if we take given climate model today, again, out of GFDL, but now rather than running it at 1/12 of a degree or 1/10 of a degree, sorry, the state of the art today is about 1/4 of a degree. This is pretty much, as much they can afford in climate modeling centers. So if you were to run the ocean only plus sea ice, you would simulate 12 years per day, and you would need about, close to 5,000 CPU cores. If you were running same resolution, 1/4 of a degree, so again, 25 kilometer by 25 kilometer horizontal resolution, for the ocean, atmosphere, land, and ice, 16, right, over, more than 5,000 CPU cores. So it's pretty expensive. At NYU, our big, cluster, it's just a little over 30,000 CPU cores. Right? So it would take a large chunk of NYU resources to have a very short, climate simulation if I wanted to do something like this. So it's quite limited in terms of compute, right? And of course, one needs access to high performance computing. So computational cost and actually access to HPC is an issue to run the simulations at higher resolution or to run them longer. So if I go back to my grand challenges, right, I still want to actually have simulations that are good enough so I can learn something new, right? So I want simulations that, I call them smart, right? They have to resolve the right scales and the right interactions so I can actually learn something new about the physics of the problem. I want them to be computationally cheap, right? I have to be able to run them fast. If I want to understand what's going on, I need to be able to play with the simulations, or if I want to explore, predictions or projections, so trying to actually go through hypothetical scenarios. And then the last one is, one that is also, almost a given. They have to generalize well, meaning if I want to trust them in different conditions and different scenarios, then they have to be robust to, my hypothetical scenarios and changes. I need to be able to trust the outcomes of the models. So they have to be good, right? They have to be fast and hopefully robust enough that I can use them widely across a wide range of scenarios. Now, that's usually where kind of one of the issue comes about, right? Because I'm limited by the amount of compute that I have, when I discretized, my equations of motions and my thermodynamics equation and so on, I'm going to be limited by the number of grid boxes that I have, right? Or the compute is going to be limited, so it's going to limit the resolution of the model, and that's going to limit the type of physics I can resolve in those models. So here's kind of a little bit of a cartoon, the way kind of climate modeling works. Take the partial differential equation, discretize them for the ocean, the atmosphere, and the rest of the Earth system component, and everything that is happening below the grid box size of your climate simulation has to be parameterized. So what does that mean? It means I need to come up with a way to represent all the processes that I can't resolve on that grid in some ways, right? And so the way we've traditionally have been doing it is by coming up with what we call parameterization. So kind of, terms that will represent the effect of clouds, turbulence in the atmosphere, in the ocean. It's going to be processes like turbulence and mixing, and try to represent their effect on, say, the large-scale transport. That is what's resolved by the climate model at the grid. So a lot of processes in climate models today are not resolved. They are parameterized. And so, as I mentioned, so cloud turbulence in the atmosphere, and also turbulence, interaction with the ice, for the ocean and so on, right? So there's a lot of things that are too small to be resolved in this kind of 25 kilometer by 25 kilometer resolution of the existing climate models today. So the parameterizations are, a big part of how we integrate simulations, but unfortunately, they are a little bit ad hoc, right? So they are kind of a representation of some missing processes onto the large-scale transport. And so the way that's been typically done in simulations, right? So that's kind of the way we run simulation. We start with a given state. We resolved, our partial differential equations, which are the physics, on the grid. Then we add a parameterization that represents the unresolved physics. We add some forcing, obviously, right? That represents kind of the external pacing of, say, the ocean. And then we predict the next state, right? This is kind of the cartoonish version of an ocean or a climate simulation overall. So some resolved physics, some parameterization for the unresolved processes, the forcing, and then I predict what comes next. And then we keep running the numerical integrators like this for a long time.
So, question.
Yes, yes, please.
For context, when you say unresolved physics and parameterizations, what, I guess, family of functions or models are you referring to?
Yes, okay. So here, for example, for ocean turbulence, we're going to end up with something that's going to be trying to actually represent mixing by turbulence on the large-scale transport. So that's what we're thinking about. So we're going to think about an ad hoc function that we can write it mathematically with some parameters that are tunable. But it's not going to be learned from data, or it might be tuned with data, but it's usually basically kind of a way from domain scientists to try to represent the effect of unresolved scale on the resolved scale.
Right.
Does that make sense?
It does, yeah.
Yeah, great. So, and that's kind of the crux, right? Is that we need to come up with a simple theory, which is usually an approximation of the effect of unresolved on the resolved scale. And now that, of course, it's imperfect, right? You don't have the right resolution, so you try to replace it with, again, some representation of the unresolved physics. Then you run your simulation and you try to compare, say, its climatology, so it's time mean state, to the observations. And as you can imagine, you end up with errors. One error is because your model is kind of a discretized version of the real world, and two, because there's not enough resolution and a lot of approximation in the model. So if we compare the 40-year time mean temperature, observed temperature, to that of the simulation, then this is what it would look like. So we call that the model error, the climatological model error. When it's red, it means that the model is too warm compared to the observation. Where it's blue, that means that the model is too cold. Sorry, I actually forgot to put a color bar, but just to give you an order of magnitude, the warming along the Gulf Stream would be several degrees, and the same for the cooling in the North Atlantic. So the model are way too warm along the Gulf Stream and way too cold in the North Atlantic. And you can pick other regions of the world. The models have those biases. They have those errors compared to the observations, again, in great part because we're not resolving all the physics, and some of the representation of the unresolved physics on the large scale is unfortunately inaccurate in some instances, right? So how can we make our model better? How can we make the Gulf Stream not overly warm and the North Atlantic not overly cold compared to observation? What is missing? And so one of the key ingredients that is missing is that the transport along the Gulf Stream and into the North Atlantic is actually too weak in existing climate simulation. So we're missing the energy that comes from those turbulent scale that re-inject momentum and energy into the flow to accelerate the flow. And again, one of the reasons is because a lot of those parameterizations are a little bit too diffusive on the large-scale transport. So one idea, obviously, in the age of AI is, can we use data to, rather than approximate those functions, those parameterization, can we just machine learn them, right? Can we use data and directly learn what's missing from the simulation using data to represent all this unresolved scale, rather than just coming up with some, again, approximate family of function that we believe will be a good representation. And so that has been going on in this world of what we call the hybrid physics AI climate modeling. So you keep the physics model by itself and add a data-driven parameterization. So I think I hear a question, right?
Yeah, the both.
Yes.
Hi. Yes.
Hi.
So I had a question about the unresolved physics. So,
Sure.
for example, like, is that something like you take the smallest grid cell and have your largest eddy or largest vortex of be of that size? So are we talking about physics that are smaller than the grid
Correct.
cell?
Yeah, that's correct. So I mean, I'm saying that in a kind of rather crude way, but yes, we're going to think about the scale that are smaller than the effective scale of the grid box size that we have. Correct, both in the horizontal and vertical, to be honest.
Thank you.
Yeah. Okay. Great. Yeah. Feel free to interrupt. By the way, this is great. So, being online is always interesting. So I welcome the interruptions. Okay. So Indeed. So we're going to actually kind of try to represent from data the effect of those, again, unresolved scale onto the large scale. But yeah, rather than approximating them by ourselves, we're just going to let, AI or machine learning basically kind of figure this out. And so I want to point out that obviously, there's a lot of efforts going on, and one of them actually at Google, right? So Neural GCM really kind of, has kind of the same spirit of building a physics AI climate model. And so what, Neural GCM is doing, which is a little bit different than what we're trying to do, and I'll explain the difference later, but it's the same flavor. We start with an initial state. There is the dynamical core that solves, again, kind of the fluid dynamics. There's a neural network that represents all the subgrid physics. Everything goes into the solver, and then we get the next time step. So here, again, the workflow, so to speak, is the same. But rather than thinking about all the unresolved processes in one go, we actually try to separate the impact of different type of, unresolved scale onto the large scale transport, because we're trying to actually understand as well the type of physics that is missing and what it's doing on the large scale transport. So really kind of going back to the understanding. So we pick one subgrid physics process. Those are called mesoscale eddies. They have 10 to 100 kilometer horizontal scale roughly. They're derived from, the instability of the currents. And again, they have these properties that they can re-inject energy and momentum into the large scale transport. And so we're going to take data. Now, that's a big part of what I'm talking about, is the data is not going to come from observations. And one of the issues, because actually in the ocean, we don't have enough observations to actually calculate those kind of unresolved scale onto the large scale transport. So what we're going to do is we're going to take simulations, run at very high resolution, and we're going to take many of them. And then we're going to filter them, coarse grain them, and diagnose kind of the missing turbulence that a coarse resolution model would be missing. And that's what we machine learn. So we take data that comes out of simulators, so out of numerical models, run at much higher resolution than, the climate models that we're trying to implement now. So, we're hoping to ingest observations one day, but again, we're pretty limited right now with what we have. So we use our ground truth, very high resolution simulations. And that's what we do. So we're going to take, we're going to basically machine learn the effect of ocean mesoscale eddies on the large scale transport using a neural network. The input is going to come from state variables, but kind of slightly modified. So we're going to use basically, I would say variables or functions of the state variables that are relevant for the turbulence. And it's going to be stress, strain, and vorticity. So they are just basically, you can think about, first order derivatives of the velocities. They give me an indication on basically the direction of momentum and energy transport locally. Put a neural network, right? And then output the parameterization. But again, in this case, it's a neural network. So I don't know exactly what the function looks like, but it's a function with a lot of parameters. We try to build them locally, by the way. So we use a very simple neural network in this case. We done many of them, right? We went from, CNNs all the way to multi-layer perceptron. Because the effect is actually relatively local, anything that is actually on a small stencil, they give us a pretty good job, give us a pretty good result and did a good job in the simulation. But what I wanted to highlight is that unlike regular kind of machine learning tasks where usually you take your inputs, right, and output, you're trying to train a neural network on it, all you have to do is to, basically standardize your input and output by just removing the mean and scaling by standard deviation. For the type of problem that we're doing, if we want them to generalize across different scales, different resolution, different depth, different type of turbulence regime, that's usually not enough. And that has been kind of one of the big ingredients that we've been trying to push forward, which is trying to think about the way we do the dimensional scaling. And for that, we've been, being inspired by what we call Buckingham pi theorem, which is basically using the units of the different variables that we care about to do a local non-dimensionalization. So here's the truth diagnosed from a high-resolution model of the effect of turbulent eddies on the large-scale flow. This is what would be, and the one on the right would be what would be predicted without the dynamical scaling. So the typical way that you would do a simple machine learning, input-output normalization. So the pattern looks quite similar, right? But the magnitude is a little bit off, and there are several regions where it's not. If we use what we call our kind of physical rescaling, so you can see that already, the prediction is a lot better than without it. But what's interesting is that if we try to translate our prediction into a model at different resolution or a different target, so that would be the truth, that would be the prediction without, retraining, right? And that's the one with the simple normalization. So overall, hopefully you can see that with the dynamical scaling, the generalization is much better than without it. And so that has been something that came from, multiple projects. By the way, it's not just us, right? So there have been kind of several of us at this kind of interface between physics and AI, showing that the way we use, the local information for the non-dimensionalization is actually absolutely critical when it comes to generalization. A lot more than the type of architecture you're going to use, or the type of function that you're going to use. And so that has been kind of a big, revelation to some extent. Maybe it was trivial, but compared to a lot of the typical machine learning, where the standardization is relatively straightforward, for us, when it comes to generalization, being able to actually collapse the conditional probability in a way that is less sensitive to changes in regimes has really kind of been massively beneficial overall. So then we can translate that across different scales. Yes, please.
Yeah, just to clarify what the idea is. At the surface, there's the very standard idea where you want to squish all values between 0 and 1 just so neural nets are happy. But it sounds like you're talking about dynamic scaling. So it sounds like what you have is if I may say crudely, a base model that says what normal is, and you scale everything relative to normal all the time, but the base model is a dynamic model of normality.
That's correct, yes. And so the dynamics come basically from the local variables that keep changing. So the normal change relative to the local conditions that you have.
So now, a stability question. If I hear the way you're saying it right now, it sounds like you're running a simulation, figuring out what's normal, adjusting all values to fit within that normal and keep going, which is a cyclical process that can go unstable. Or you can say here's a separate simulation that's just coarse and cheap, and use that for normalization, and that's at least a stable anchor, but it's coarse, so maybe flawed.
Okay, yeah, so all right, so let me clarify that. So right now, all the normalization is done offline. So all the training is done offline, all of it is done with a given simulation for which we do it. So that's where we're at. Then we plug it into a climate model. And so now we're actually using the local variables that are changing, and actually, it's very stable. So when we plug it into a climate model and we look at the response on the large-scale transport, say, for example, this used to be our big error in temperature. The Gulf Stream was too warm, then in the North Atlantic, too cold. So we run our new simulation with our machine learning. Again, the input outputs are normalized based on the local value of the coarse resolution model in which we're inputting the new parameterization. And this is the response that we get, so not the old bias. So where it was too warm, now the response of our neural network is to cool the Gulf Stream and then to warm it where it was too cold. So if you sum them up, basically the error is being reduced. And one of the reasons is because the large-scale transport in the Atlantic is actually improved through energetics that comes from those unresolved physics that are now better captured by the data-driven models that they were before. But it's still, a numerical solver plus the parameterization. Yes, please.
Sorry again. It's a little noisy here, probably. But I was curious about how, like, when you add closure using a neural network, do you impose like constraints of continuity or incompressibility?
Yes, that's a wonderful question. Yeah, I kind of skipped a little bit of the details, but the way we built the ANN is actually by design non-divergent, so it's actually conservative. So what we do, just go back, I kind of didn't mention it, but we take the divergence of a stress tensor. So the tensor is going to be symmetric. So that means actually we basically are already imposing some conservation laws. And again, the divergence makes it also kind of locally conservative. So we build them in this framework by itself. Yeah, thanks for the question.
Oh, thank you.
Yeah, right. Okay, so here, I mean, again, I kind of give you a flavor on the way we do it. We do it for multiple type of kind of subgrid physics. And what we're trying to build is models, right, that are climate models that are coarser resolution, but are better. They're more representative of the physics because rather than making an assumption about what the mystic physics look like, I just learn it directly from data. But of course, there are many challenges, right, that remains for this type of hybrid simulation. So numerical stability, so one of the questions came up. Sometimes we are lucky when we plug those kind of neural network into the model itself, and the model remains stable. Sometimes we are unlucky. But it's also true if you have physics-based parameterizations, by the way. I didn't talk about entropy quantification here, but as you can imagine, I'm learning something from data that is, not necessarily the ground truth. So we should have a way to quantify that. Out of distribution, even though we have a better, way to represent the physics, I can't model every single scale interaction in the world under every single type of regime, right? So challenges, there are many of them. I'm happy to talk about it some more, in the Q&A. But I would say the other big challenge is the development cycle is super slow, right? And the models are not accessible to all. You need a supercomputer, you need a climate modeling center that develops it. And again, then you need to implement, your parameterization in a legacy model, and all of that takes a long time. So we've been trying to think about, it's kind of the other side of the coin that comes with AI, which is, can we build full AI emulators of those climate models? Let's assume I made them better, but I still am limited with compute. Can I try to fully emulate them? End-to-end AI, kind of, input to output, no physical solver in the middle. I'm just trying to emulate the full trajectory of it. And we're hoping that it will help actually with model development, but also scientific discovery. The other thing is, of course, after we train them, anyone can use them because you just need a single GPU or even a CPU to some extent to be able to run it. So I'm going to give you a couple of examples of the type of emulators we've been building and kind of the way we're thinking about it. Again, a lot of it is work in progress, and same for the hybrid modeling, by the way. I like to talk about things that we're working on because it's good to hear questions from people. Helps us rethink as well the way we are building those tools. So we go back to this kind of diagram, right? The way we run ocean climate models. Take an ocean state, we solve the PDEs, we add our parameterization, whether they're physics-based or ML-based. We have some forcing, we predict the next step. So now what we're going to do is the data is still going to come from the numerical simulator, but we're going to fully replace the solver and the parameterization with a big neural network, right? So that's going to be the goal. Given, input output, which are the prediction states, just replace the entire core with a machine learning model. The advantages of those kind of cheap emulators, right? One, they're cheap. Even though they have a lot of parameters, they're still, kind of reduced all their models. So I can do an exploration of mechanisms at many scale because I can run many of them. I can run very, very long simulations, right? I can have large ensemble size if I want to do extreme event, or if I want to do data simulation where I merge, simulations and data together. And so we've been building those emulators now for, 2 years or something like this. And so I'll show you a couple of examples on kind of the way we're approaching the problem. So we're going to start with an ocean-only model, kind of the same one that we've been using for the hybrid simulations. We're going to use the data that comes, directly from that simulation, which basically for the ocean solves partial differential equations for sea surface height, U, which is the horizontal, U and V, which are the horizontal velocity components of the ocean at every single depth in the model, temperature and salinity, same thing at every single depth in the ocean at a given time. As mentioned, we're going to have some forcing at the surface that kind of, drives the ocean. The simulation is 60 years. And again, the prediction are the state variables at the next time step. So here's just the global mean temperature of the ocean to just show you the train validation and test sets that we're using. So the ocean usually kind of at the start of the simulation kind of adjusts to its own climate and then feels the forcing. So you can see basically, kind of the annual cycle and then some variability and some trends. So we're going to train and validate over this portion here, and we're going to test in the latest part where the ocean warming is a little bit more, or is a little bit faster actually than just before. Okay, so a little bit more granular view of what we're doing. So our full ocean emulator is called Samudra. So as I mentioned, we're going to use the state variables of the oceans themselves, but our input is going to be the current time step and the previous one, and the output is going to be the next 2 time steps. So we call it 2 in, 2 out prediction. And we can think about it as kind of learning the rate of change of the variables and predicting, right, given the rate of change before. So you can think about this as accelerations or tendencies of the models. Now, we were faced with 2 challenges. One is, even though I keep telling you, oh, those coarse resolutions are bad and are coarse, it's still a lot of data, right? It's quarter of a degree simulations that I need 60 years of simulations for. So we had to actually downsize the data because there's actually nowhere for us to save it. So the data was coarse grained onto an horizontal grid of 1 degree. And then we take 5 days averages of the variables, right? So it's a massive kind of, model reduction already. And then we went down to 19 vertical levels from, now I forgot if it's 42, 73. Sorry, we're using so many models now that I forgot. But still also a pretty big downsize in the number of vertical levels. And we do that in a conservative regridding because we want to make sure that all the quantities that we care about are still conserved, right? This is important at the end of the day. But it's a big model reduction size in terms of the state vectors that we have. And then in the middle, the machine learning architecture that we've been using and that we published with is basically a UNet, slightly modified, so it convex UNet. Number of parameter, 135 millions. I should mention that we've tried several other architectures. We tried swing transformers as well. We tried different type of UNet or CNNs. We saw marginal changes, I must admit, depending on the type of architecture. We believe it's, one of the reasons is we kind of limited with the amount of data that we have. And as I mentioned before, we basically have a training set, 75 to 2012, validation and inference. Yes.
Hi. So in the state variables that are being simulated in the model, what are all the state variables?
Those are, so for the oceans, that's all the state variables. So they are those that I'm listing here and that we're also emulating. They are the one for which we would have a partial differential equation that is being time-stepped that is being time-stepped. Everything else is being inferred. So let's say vertical velocity will be inferred from the horizontal velocity using continuity.
Oh, so those are inferred, and
the
state
other
variables
ones are all inferred, and those are the ones that are really time-stepped in the model as well. Yes.
Actually, can you name those because those are not familiar for a lot of people?
Yeah. So SSH, sea surface height, U and V are the horizontal velocity components. T, temperature, S, salinity.
Got it.
Yeah, sure.
So are you modeling? So you have the convection, the heat and flow equations, and then you also have the transport for salinity.
Yeah, that's correct. So basically, in terms of the dynamical equations that we have, so we have basically Newton's law, right? So the momentum equations for U and V. Then we're gonna have a heat equation for temperature, a salinity equation, right? Sea surface height comes from continuity. Basically, you can think about it in this form, so kind of mass conservation as well. We have one additional equation, basically, which is the equation of states. That's not being time-stepped, and it's a relationship between pressure, temperature, salinity, density.
Oh, so is that like an additional constraint that these solutions have to obey?
Yes, that's correct. That's correct. So for the atmosphere, so the ocean is a little bit weird because we don't really have a formal equation of state. For the atmosphere, you can think about the ideal gas law, for example, right? That's usually the equation we would use. Yeah.
Oh,
that makes sense? Great. Yeah, thanks for your questions. Okay, good. So I'm glad that clarifies this. And so, yeah, basically, UNet architectures, lot of parameters. So this is kind of the model. Again, just written very simply mathematically. This is our our kind of two model out. F is neural network, previous to time step. Tau is the atmospheric forcing that we're using. So again, just in a cartoonish way, the inputs and outputs are going to be the states of the ocean, the velocities, the temperature, the salinity, the sea surface heights, given surface forcing. The neural network, again, a big unit. Our loss function is very, very simple, right? There's basically 4 recursive time step, because the time step, as I mentioned, are coarse grain 5 days averages of the state vector. I'm going to do 4 recursive time steps, so we can think about basically mean square error loss that accumulates over those kind of 4 time steps. So that means 20 days roughly. And again, it's for basically a cumulative loss function for the different state variable. I have nothing else in there, right? I have no additional constraint. You can see I have no additional regularization. We keep it as simple as possible. It has, of course, its downsides, and I'm going to come back to it in a bit. But so 2 in, 2 out for the main state variables of the ocean, loss function that is just over 4 recursive time steps. And again, the forcing comes again from the ocean model, the atmosphere. So here, after again, kind of, training validation, here's the inference in the last 8 years of the simulation. So the top left is the ground truth temperature. So this is depth. This is latitude. So what you see here, this kind of bowl shape is kind of the typical bowl that we would expect the temperature to look like, meaning it's kind of warmer near the surface and it gets a lot colder as you go deep into the ocean, obviously, because there is no sources of heat that comes from the atmosphere. So this is the ground truth in the Atlantic. This one over here is Samudra prediction, right? So those are kind of time mean. In all honesty, the first time I saw the Samudra prediction, I could not have told you that it was, a data-driven model. I can't distinguish between the truth that comes from the numerical simulator and the one that was emulated overall. So it's pretty good, but of course, it's a time averaging, right? If we try to look a little bit more carefully, right, about, oops, I don't know what happened. You see. Is that back?
Yeah.
Yeah? Okay. Yeah. Yeah, I tried to play the movie, but kind of decided to stop. All right, there we go. So here on the top is this, both of them are temperature variability in the tropical Pacific. So this kind of ENSO variability, right? So this mode of variability in the tropical Pacific. We're looking at depth, longitude now. So we are along the tropics. And Samudra is on top. At the bottom is the ground truth from the numerical model. And what you see are basically waves propagating along the tropics, warm and cold waves. So kind of, they mimic the interface heights, of the ocean. Again, a signature of ENSO variability. Same thing. It's hard to tell which one is the emulation and which one is the model. This is surely not perfect, right? Meaning that the emulation is not a perfect representation of the ground truth, but the variability is quite, realistic overall. Now, not everything is great. First, I'm going to tell you a couple of good things still, but then I'll tell you a couple of bad things with Samudra. So we built 2 types of emulators. One, the one that I just described before, that has the 5 kind of, time stepping variables that the climate model has. Sea surface height, velocities, temperature, and salinity. We call that the thermo plus dynamics, model. And that's the green line here as a function of time. If I take a forcing and I keep repeating it, then basically Samudra can run for centuries and be completely, stable if you want, right? And so that's good news. I can do the same, but now if I remove the velocity, I call that the thermodynamics. I remove the dynamics if you want. Again, I can run it for centuries. But hopefully you can see the difference in the 2 time series, right? The one at the bottom that has U and V in it has a lot of kind of, little high frequency variability, which actually technically is not present in the model itself. And that's going to become one of the challenges that I'm going to describe in a second. But again, still staying on the good news, the emulation can run stably for hundreds of years. So that means I can build kind of an ocean emulator that is stable for hundreds of years, which is great. Yes.
Oh, another question. So along the stability, 2 questions, I guess. So first one, if you don't have an external forcing, is the system dissipative? Like, does it all dissipate out?
Yeah, so that's a great question. So yes, if we were to think about a typical kind of fluid problem, if I had no external forcing, then I would expect that at some point I would basically kind of settle into basically into a dissipative kind of state, right? If there is no additional forcing, at some point something will kind of go away. Here, the type of forcing that we're talking about as right, is both momentum, heat, and fresh water. So we are exciting both the momentum and the thermodynamics aspect of it.
Oh, okay, thank you.
Yeah.
And
Sure. Yes.
second question. So this time plot of
Yes.
temperature, is this how it's supposed to be like when you run the simulation? Is it quasi-static or is it like growing over time?
Yes, I'm going to come back to it. All right. Hold
Okay,
on for a couple of slides. Thanks.
Okay.
They're great questions, by the way. Yeah. Okay, let me give you 2 words first on the computational costs. So the original OM4, again, that's as we said before, right? It's a little bit over a decade, almost 5,000 CPU cores. Samudra, the new version, actually, we've been working with OpenAthena, which are software engineers helping us to both accelerate and develop new models. Now we are 4,000 simulated years per day on one A100, right? So this is kind of cool. You can do a lot computationally. We've been building a new AI emulator now that includes the ocean, the atmosphere, the sea ice. So I'm just going to give you a quick overview of it before closing with some of the challenges. So if I take a full climate model, right, so now ocean, atmosphere, land, ice, right, so as we mentioned, still over 5,000 CPU cores, 16 simulated years per day. We built Samudras, again, that is a few hundred times faster than the original model on one GPU. So this is kind of some nice little animations of the emulators that we're building. So now not just the ocean, but the atmosphere as well. So I'll just show you a couple of slides on the coupled emulator. And then I'm going to close with some of the challenges, which will bring back the question about the trends and is the simulation supposed to look the way that it looks. So I'll tell you, so this was released, I think a week or 2 ago, not more than that. So again, all those things are still very much work in progress. So what we've been doing is to actually train the coupled emulators separately, meaning we trained an AI emulator for the ocean by itself, one for the atmosphere by itself, and then we coupled them. So this is the way that typically climate models are also being developed, each component by itself, and then they are coupled. And we found that to actually be more reliable, to exchange the fluxes in this way, so that, again, kind of the emulators learned, if you want, a ground truth before they get coupled with some of the imperfection of each other. So we found that to actually be an important step in the coupling procedure. We've been exploring a few ideas there, but so far it's been kind of the most successful to build the emulator. Now, a couple of things I want to mention. Sorry, one sec. One thing I want to mention is the atmosphere is being time-stepped over 6 hours, while the ocean is 5 days. So we also had to make sure that, the 5 days that the ocean kind of is taking its time until it connects to the atmosphere is also kind of conservative, and the same way the atmosphere accumulates the fluxes is over the 5 days. Yes, please.
Oh yeah. Is this, so you're comparing this to a trained ocean with a static forcing of atmosphere, and atmosphere with a static forcing of ocean, not an coupled integrated climate ocean model is trained as a unit. Is that,
that's correct. So the climate simulation is fully coupled, ocean, atmosphere, ice, the whole shebang. But for our AI emulators, we don't train over the full state. We basically train them separately. Ocean only with the given atmospheric forcing, atmosphere only given the ocean surface forcing. Yes. And then after we pre-trained each component, we basically fine-tune them together.
And have you tried unified training, like trying to understand the stability trade-offs?
Yeah, so we have one of the biggest issues we've been facing so far is that because the timescales of the oceans are so slow compared to that of the atmosphere, and also the spatial scales of oceans and atmosphere are so different, we find it actually extremely hard to get the coupling at the, at the interface to be learned correctly. And that made the emulators worse. And that's why we kind of went with that kind of separation of components and then fine-tuning after we pre-trained them.
So that's actually a generalizable lesson. Yeah, when you have
definitely
space scales, or maybe different, like thinking ecological models, very different species,
exactly.
You don't want to call training. You probably want to have these separators. Okay.
Yes, or at least, again, that's what we found here, and we see that across the board in several applications. So that's definitely been a lesson learned for us. Yeah, thanks for the question. So this ENSO viability, right? So what I showed you for the ocean only was forced by the atmosphere. So you could say, well, I cheated because I gave it a lot of the forcing already that would drive El Nino, which would have been a fair comment. Now, in a full coupled AI emulators, there is no more cheating, because now, after we fine-tune them, then we basically fully emulate them. There is no more, forcing that I'm imposing. It's a complete self, interaction of the different components by themselves. And here we're seeing kind of different initial conditions of the emulator, so each one of those lines, which generate basically some ENSO viability that looks right. And in this case, it was trained on pre-industrial control, meaning there should be no trends. It should be kind of on average, it should be flat, just a lot of fluctuations around it. And, the type of viability and periodicity that we get is about right compared to the original model. The precipitation associated with the ENSO viability is also quite similar to the original model, with still some errors, right? In some places, it doesn't precipitate as much compared to other places. So, but all in all, we still remain within the bulk viability of the original, simulator, despite, again, smoothing some of the data, despite, having this kind of pre-training, then only fine-tuning later. So, despite all of the issues, it's still, does a pretty decent job, and it does it fast. The other thing that we could do, as well, was to look at the large-scale ocean circulation now, because we can run for hundreds of years, very cheaply. So this circulation is basically the transport of warm water to high latitude that sinks at depth and then return, right? It basically kind of, it's kind of as a decadal to centennial timescale. That's a mood race. That's the original model. That's the error. So it has some errors, no doubt about it, right? The errors can reach about 20% in some places. But the type of viability that we get, again, is, comparable to the original model. So as I said, those models are very, very new. We're still very much in the development phase. But, we see some good indication. And again, a lot of lesson learned, as mentioned, by Greg, right? When you have different time scales, different, spatial scales as well, the way we build the models, the way we non-dimensionalize everything, the way we couple them has been an older one, part of the lesson of building those emulators. So now I want to go back to the question about, for the ocean one. And because I want to kind of give you again those 2 points, which I think are important when we think about kind of learning physics overall. So for the ocean, and like for the coupled emulators, indeed, I learned, over, a training set that had some warming trends. And then I rolled it out over a test set that also had a warming trend. But Samudra could not capture that. So here's the global mean temperature as a function of time over the test sets. The black line is the global mean temperature of the ocean simulation, the original one. And the 2 emulators that we trained, the thermodynamics and the thermo plus dynamics, in both cases do not show a trend, right? They're actually quite stable overall. We tried, several ways to train it. We tried to add regularization, to add global conservations. We always found a trade-off. In some of the models, I could capture the trend over the test set, but then if I try to roll it out longer, to just try to do some hypothetical scenario, then the model will go unstable, right? It would then roll instably after a few decades. And it can only run stably for hundreds of years if it doesn't capture the trend. So basically what we're finding here, and again, we see that in multiple emulators, whether they are for the ocean, the atmosphere, and the ice, if they're stable, they become insensitive to perturbation, meaning you need to hit them hard for them to respond, but they usually don't respond with the right magnitude. They're too muted. And that remains a challenge. And if they're not muted, then usually, again, they're too sensitive and they become unstable very quickly. And so I think this is, a lot of people came up, including ourselves, with some possible fixes, but those are still pretty ad hoc. So we're trying to explore how to make them conservative at the grid box level, like a numerical model, to maybe, make them more sensitive and not too sensitive, rather than have ad hoc global constraints. Still work in progress. I can't tell you anything about it because we don't know yet. We're just kind of trying to formulate the problem, but we think that might help. The second point is the point that was raised before, the imprinting of the fast variability on the slow variables. And that's kind of a lot of the noise that you see in the emulator compared to the original global model. So there we've been working again with OpenAthena to modify the loss function and also use wider networks. So that has helped on the kind of spatial imprinting, but not for the temporal one. So that's why kind of the separations of scales has been quite useful for us. So those are, I would say, really the key challenges that we've been facing and that we still kind of don't know how to solve, because we want to use those models, as I mentioned, to understand the physics, but also to be able to actually make predictions overall. So there's still, some way away. If you're interested, everything we do is, online, open source. You can use as many things as you want. The team is formidable. And thanks again for your question. I think there's still a few minutes left for some questions, if anyone has any. Thanks again.
Yeah, well, thank you very much. So, one obvious question is, when can we use this? Because I see, for example, you have some of these M2 lines things. Samudra is available on the Allen Institute, I noticed, but I'm not sure how much of this is usable by the community.
Yeah, so Samudrace, and another AI emulator called Camulator, all of that are open source. The weights are on Hugging Face. The code is also on our GitHub. All of that is open. The hybrids, AI plus, physics are also available online on the M2 Online GitHub. Those, of course, are a little bit harder to run because, those are kind of legacy models. But the AI network, the subgrid parameterization, weights are online, open. Yeah, everything is usable.
Okay, fantastic. And are there also the forcings available for them? Or I guess how
forcings are available. Yeah, forcings are available as well.
Should we be thinking of these as probabilistic models? Like should be like distribution of the possible climates, I guess.
That's a good question. And I didn't talk about this, and I probably should have. Right now, we've been building everything in this kind of deterministic world where we have a given forcing and, weights that are trained in that deterministic way. Our next step is definitely moving toward probabilistic ones. Yes.
Thank you.
Yeah, right. Thanks for that.
Thank you, Laure, for the great talk.
Thank you.
I really like the talk. I have a couple of questions. So, on the previous slide where you showed the averages. So, first question is are these spatial global averages?
Yes.
At that time step.
Yeah, so those are full 3D global average. So it's the full ocean temperature average, every single grid box, every single layers. Yeah.
So I'm wondering almost if the seeming stochasticity at each time step, I'm wondering if it's because of some artifact, because you're taking a state and then getting a forecast, getting an estimate for the next time steps using the neural network, and then basically running this iteratively over and over again. So I'm wondering almost if a more continuous or a recurrent based formulation like an RNN or even a neural ODE could smooth out that in time.
That's a good question. Yeah, that's a good question. I have to admit we haven't tried it. There is definitely accumulation of errors, right? That's a given. But the major issues that we find is really that, I haven't shown that, and I'm sorry, I should have done that. If I give you a map of temperature that comes out of the emulator, even after one time step, you're going to see a lot of small scale structures that looks like the velocity, when technically temperature is a lot smoother than velocity. So we get this imprinting, and I think it's in the training. I don't think it's in I think it's not in the rolling of the emulator. I think it's again this kind of, because the loss function is basically kind of, taking all those things together. And, I mean, as you know, I don't need to tell you, we're minimizing a loss. So it just gives you the minimum that it will get, but sometimes it kind of mixes up the different scales.
Another question. So the lack of stationarity, or it's almost like physical systems, especially the driven ones, that they may not always be like measure preserving over time. So like things grow.
Correct.
Whereas it's almost like a pathological thing with machine learning based methods, where a number of popular ones almost like do not show things like this, and they're very quasi stationary. So do you think it's because of the way the model is that you don't see this growing, like a sense of expanding in the state? Or is it because like a state in here is not forcing it, like maybe global warming?
That's a good question, right? So there is a warming trend in the original data that we train on. So I don't know. I think I have many hypotheses, to be perfectly honest. If you ask me at different time, I'll tell you one is more important than the other. One is we're only training over short time windows, right? 20 days. There's a lot of ocean variability, and that small trend, because the trend is tiny, right? If you look at the magnitude, it's tiny. And the fluctuations on 20-day time step are very large. So I think the network is only learning what it's supposed to learn, which are the large fluctuations. And it's harder to pick up the small ones that will emerge over a long amount of time. So I think part of it is the way the training is done. The other part is, I think, because we're doing so much kind of, collapse of the state variable onto a reduced, order model, if you want, we're losing some of the conservative properties of the local scale. And so that means I'm not enforcing something that I know for a fact. If something is conservative and I add a forcing, then the net change will be the forcing. But here, because I cut a lot of things off, I'm only approximating the conservation. So then it's harder to actually pick it up when you put a forcing. So I think those are the two things I would say are where we need to fix something. I think more than the model itself, to be honest. But I might be wrong.
Because I imagine the observables that we have, like you have here, the velocities and all the transport equations, something like rising global temperatures. I imagine if you simulated this system in isolation, the temperatures may not rise. Whereas if you have like global warming and increasing CO2 concentrations and all of these effects, do you think that these observables not being part of the simulation is?
I mean, again, right, as mentioned, so it's trained on a simulation that has a forcing, that has a global warming in it, right? So it's more than not being in a training set.
Oh, okay. Greg, you had a question?
Yeah. I probably hopefully last one because I think we're taking up too much of your time. But I'm noticing what you're saying is you have a limited data on the global climate system, but I'm observing there's a lot of data on hydrology, different salinity levels and so on from lab, from lakes. I mean,
yes,
limited, but your control remains. Is that usable?
Yeah, so this is my dream, by the way. So we started with models both because of, again, the lack of observations, but also the fact that I can control the experiment, right? I can kind of remove one part of the uncertainty. But what I would love to do, and I really, really, really hope we're going to do that, over the next, year or so, is to try to find a way to ingest a lot of those observables that can be used either as constraints or, to refine the model. I don't have enough to train just on the data itself, but then can I pre-train, right, on imperfect simulated data and then fine-tune on the observable? So yeah, I think there's a lot of data out there that is usable. How to do it, that's going to be kind of the big question, to have this kind of mixture of data sets. Yeah, thanks for the question. Great question.
Thank you. Well, so I think we're already past time, so probably do additional offline. Yeah, but thank you, Laura. This is fantastic. And yeah, the tools
Thank you so much.
Thank you.